The bridge should not have been built. Not in the way it was built, not on the timeline it was built, not by the people who actually built it. Every reasonable assessment of the Brooklyn Bridge project in 1872, 4 years after construction had begun, 2 years after the chief engineer had been incapacitated by an injury that left him bedridden for the remainder of the project, would have concluded that the work should stop, that the money should stop flowing, that the partially completed towers rising from the East River should be abandoned to weather and politics and the accumulated weight of a decade of complications. The assessments were made, the conclusions were drawn, the money was repeatedly threatened, the politics were repeatedly hostile, the towers continued to rise. They continued because of a woman who has been described in the historical accounts that gave her any attention at all as a devoted wife who carried messages between her incapacitated husband and the bridge's construction staff, a helpmate, a conduit, a loyal companion who made herself useful in a supporting role while the real engineering was done by others. This description is not false in its individual components. Emily Warren Roebling did carry messages. She was devoted to her husband. She did make herself useful. It omits, with a completeness that requires. The bridge should not have been built. Not in the way it was built, not on the timeline it was built, not by the people who actually built it. Every reasonable assessment of the Brooklyn Bridge project in 1872, 4 years after construction had begun, 2 years after the chief engineer had been incapacitated by an injury that left him bedridden for the remainder of the project, would have concluded that the work should stop, that the money should stop flowing, that the partially completed towers rising from the East River should be abandoned to weather and politics and the accumulated weight of a decade of complications. The assessments were made, the conclusions were drawn, the money was repeatedly threatened, the politics were repeatedly hostile, the towers continued to rise. They continued because of a woman who has been described in the historical accounts that gave her any attention at all as a devoted wife who carried messages between her incapacitated husband and the bridge's construction staff, a helpmate, a conduit, a loyal companion who made herself useful in a supporting role while the real engineering was done by others. This description is not false in its individual components. Emily Warren Roebling did carry messages. She was devoted to her husband. She did make herself useful. It omits, with a completeness that requires deliberate effort to explain as anything other than intention, the fact that she taught herself higher mathematics, the theory of cable construction, the properties of steel wire, the calculations of catenary curves, and the principles of structural load analysis, that she supervised construction directly, that she negotiated with politicians and suppliers and skeptical engineers, that she was the effective chief engineer of the Brooklyn Bridge for 11 of its 14-year construction period. The notebooks she kept during those 11 years have been held at Rutgers University's special collection since 1966, donated by her descendants after the family recognized that what they contained was not personal correspondence, but a working technical record of the bridge's construction. The notebooks are written in a hand that changes over the 11 years. The early volumes show the careful penmanship of a woman transcribing technical information she is learning. The later volumes show the confident notations of an engineer who has been working with these concepts for a decade and no longer needs to write them out carefully because she knows them. The change in the handwriting is the change in the person. The notebooks are the evidence that the historical description had always missed. America in 1869 was building across its rivers with an ambition that matched the ambition it was bringing to everything else: the transcontinental railroad, the steel industry, the industrial expansion that was transforming a largely agricultural country into the most powerful manufacturing economy on Earth. The East River crossing between Manhattan and Brooklyn was the engineering problem that Brooklyn's boosters had been discussing since the 1850s. The East River was not technically a river.
It was a tidal strait connecting upper New York Bay with Long Island Sound, and its tidal currents and its ice were problems for the ferry service that was the only available crossing. The ferries worked. They did not work in ice storms. They did not work when the tidal currents were at their worst. They were inadequate for the volume of traffic that the growing populations of Manhattan and Brooklyn were generating. John Augustus Roebling understood bridge engineering as no other American did in 1869. His wire rope manufacturing company in Trenton, New Jersey, had made the cables for every significant suspension bridge built in the United States since the 1840s. He had designed and built the Niagara Falls Rail Bridge, the Cincinnati-Covington Bridge over the Ohio River, and a series of smaller spans that had established him as the preeminent practitioner of suspension bridge engineering in the country. His design for the Brooklyn Bridge was audacious, a main span of 1,595 feet, longer than any suspension bridge ever built, longer than seemed physically possible to most engineers who reviewed the proposal. Two masonry towers 276 feet above high water, foundations sunk to bedrock through caissons pressurized with compressed air. 4 main cables, each containing 5,282 wires of steel, carrying a deck that would accommodate 2 railroad tracks, 2 roadways for horse-drawn vehicles, and a central pedestrian promenade. The proposal was approved, and construction began in 1869. 3 weeks after the first preliminary work began, John Roebling was on the Fulton Ferry Dock in Brooklyn making survey observations when an incoming ferry crushed his foot against the dock piling. The injury was severe. Tetanus set in within days. He died on July 22, 1869, 13 days after the accident. His son, Washington Roebling, took over as chief engineer. Washington had worked alongside his father on the Cincinnati Bridge and had trained as a civil engineer at Rensselaer Polytechnic Institute. He was 32 years old when he took charge of the most ambitious bridge project in American history. He had been married for 3 years to Emily Warren Roebling, a woman from Cold Spring, New York, the sister of his commanding officer from the Civil War, whom he had met at a military ball in 1864 and married in 1865. Emily Warren Roebling had received the formal education available to women of her era and class. She had attended Georgetown Visitation Convent, one of the better schools for women, but not an engineering education. There was no engineering education available to women in America in 1869. She would need one.
The caisson disease that incapacitated Washington Roebling in 1872 was not understood as a disease when it struck him. The compressed air caissons that were being used to sink the bridge's foundations to bedrock were the most dangerous environment that 19th century construction workers regularly entered. The caissons were large wooden chambers, open at the bottom and pressurized with compressed air to keep water out while workers excavated the riverbed above the bedrock. The pressure inside a caisson working at significant depth was substantially above atmospheric, enough above atmospheric that the physiology of breathing compressed air for hours and then returning to normal atmospheric pressure produced effects that were catastrophic and incomprehensible. The workers who ascended too quickly from the high-pressure caissons experienced what they called the bends, excruciating joint pain, paralysis, sometimes death. The physicians who attended them had no framework for understanding what was happening. The connection between compressed air exposure and the symptoms was recognized empirically, but the mechanism, nitrogen bubbles forming in the blood and tissues during decompression, would not be understood until 1878, when the French physiologist Paul Bert published his foundational work on caisson disease. Washington Roebling had spent months in the caissons, supervising the work directly, breathing compressed air, ascending and descending multiple times daily, in conditions that subjected his body to repeated decompression stress. By 1872, his health had been destroyed. He suffered from extreme sensitivity to light and sound, severe muscular weakness, and neurological symptoms that made sustained work impossible. He was confined to his home in Brooklyn Heights, from which he could see the bridge towers rising across the river through a telescope. The engineering work had to continue. The bridge was committed. The funding, the political capital, the partially constructed towers, the reputation of the Roebling family and the Roebling company that was supplying the wire. Stopping was not actually an option, though it was repeatedly discussed as an option by the politicians who controlled the funding and who periodically used the chief engineer's incapacity as leverage in negotiations about project costs. Washington could work in limited bursts. He could review documents, make calculations, provide direction on specific technical questions when his health permitted. What he could not do was what a chief engineer was actually required to do: be present at the construction site, supervise the work directly, make the hundreds of day-to-day decisions that the progress of construction required. Emily Roebling made herself into the person who could do these things. The self-education that Emily undertook between 1872 and 1877 is documented in the early volumes of the Rutgers notebooks and in her correspondence from the period, some of which has been preserved and some of which has been lost. The documentation shows a systematic program, not a casual acquaintance. She began with the mathematical foundations, algebra, analytical geometry, differential calculus, that she had not received in her formal schooling and that were prerequisites for understanding the structural analysis of a suspension bridge. She worked through textbooks, sought instruction from engineers and mathematicians who were willing to provide it, and tested her understanding against the technical documents that were accumulating around the bridge project. The structural analysis of a suspension bridge involves calculating the catenary curve taken by a hanging cable under its own weight, the modification of this curve by the loads applied to the cable through the bridge deck, and the forces transmitted through the cables to the towers and anchorages. The mathematics is not trivial. It requires understanding differential equations and the methods for solving them in the specific case of a hanging chain under distributed load. Emily worked through this mathematics in the notebooks. The early entries show her working through the derivations step by step, making errors and correcting them, building understanding incrementally. The later entries show her applying the results directly to the Brooklyn Bridge's specific geometry, calculating forces, checking specifications, identifying discrepancies between the theoretical analysis and the construction drawings. She also studied the materials. The Brooklyn Bridge's cables were steel wire, not iron wire, which had been used in previous Roebling bridges, but steel wire, which offered higher strength at lower weight, but whose properties were less well established by practice and experience. The specifications for the wire, the required tensile strength, the required ductility, the required uniformity, were critical to the bridge's safety, and the testing of wire samples as they arrived from the Roebling Company's mill was a continuous requirement. Emily learned to interpret wire testing data. She understood what a tensile test measured, how the results compared to the specification, and what variations from specification were significant and which were within the expected manufacturing range. This knowledge was not academic, it was operational. The wire testing was ongoing. The results were being compared to specifications that had been set based on theoretical analysis, and the decisions about whether to accept or reject wire based on testing results affected the schedule and the cost of the project in ways that required judgment from someone who understood the analysis behind the specifications.
Her correspondence from this period includes letters to engineers at the Roebling Company discussing wire testing methodology and specification limits. The letters are technical in content and confident in tone. They are not the letters of a layperson conveying a message from someone else. They are the letters of an engineer who has done the underlying analysis and is discussing her conclusions with other engineers.
The physical presence at the construction site that Washington's illness prevented was the requirement that Emily most directly fulfilled beginning in 1877. The construction superintendent, C.C. Martin, was a capable engineer who managed the daily operations of the project, but Martin answered to the chief engineer, and the chief engineer's direction had to come through Emily, who visited the site regularly, observed the work, and returned to Washington with technical questions, and returned to the site with technical answers. This description understates what actually happened. Emily was not a messenger. She was making engineering judgments. The notebooks from the construction period, 1877 through 1883, contained field observations, measurements, calculations, and decisions that are not transcriptions of Washington's instructions, but original technical work. She calculated the load distribution on the anchorages during the spinning process and identified a potential issue with the stress distribution that was addressed by modifying the spinning procedure. The notebook entry in which this calculation appears shows the derivation, the identification of the discrepancy, and her proposed resolution, all in her handwriting, without any annotation indicating that the calculation was Washington's or anyone else's. She also navigated the political dimensions of the project that were inseparable from the engineering dimensions. The bridge was a public project, financed by the municipal governments of New York and Brooklyn, overseen by a board of trustees that included politicians who knew nothing about engineering and who periodically used their oversight authority to create leverage in negotiations about contracts, costs, and the disposition of work among connected suppliers. The political situation in the late 1870s was particularly acute. There were members of the Bridge Board who believed that Washington Roebling should be replaced as chief engineer, that his incapacity made the position a formality, and that the actual engineering work was being done by subordinates who should be formally recognized and compensated as principals. This was not an entirely unreasonable position, but its motivation was not purely organizational. Some of the advocates for replacing Washington had connections to contractors and suppliers who believed that their position in the project would improve with different management. Emily managed this threat. She made herself the visible face of the Roebling family's involvement with the project, attending meetings, briefing trustees, writing reports, appearing at public events associated with the bridge. She made the case for Washington's continued leadership by demonstrating in her own conduct that the leadership was being exercised effectively. The trustees who met with Emily Roebling were not meeting with a proxy for her husband. They were meeting with an engineer who knew the project as well as anyone alive, who could answer technical questions in detail, and who had the political skill to manage the competing interests of the Bridge Board without providing any of them with a reason to move against the Roebling family's position. She succeeded. Washington remained chief engineer through the bridge's completion.
The wire fraud scandal of 1878 and 1879 was the most serious crisis of the construction period, and Emily's handling of it is the most direct evidence of her engineering authority on the project. J. Lloyd Hay was a wire manufacturer who had obtained a contract to supply wire for the bridge's cables. The wire was to be tested against the project's strength specifications before acceptance, and Hay's wire was regularly tested and regularly found acceptable. It was not acceptable. The testing was being corrupted. Hay was substituting acceptable wire during the testing process and supplying inferior wire for the actual construction. The substitution was discovered when independent analysis of wire samples from the cables under construction revealed that the wire's actual properties did not match the certified testing results. The discovery created a crisis that was simultaneously technical, legal, and political. The technical question was what to do about the inferior wire already installed in the cables. The legal question was how to address Hay's fraud. The political question was how to maintain public and governmental confidence in the bridge's safety when it was known that some portion of the cable wire did not meet specifications. Emily's response to the technical question was the response of an engineer. She had Washington review the structural analysis, working through his illness to perform the load calculations, and she performed independent verification of the analysis. The conclusion, reached by both of them working separately and arriving at the same result, was that the inferior wire, while not meeting the original specification, was present in quantities small enough relative to the total cable cross-section that the cable's actual strength remained within acceptable safety margins. The safety factor built into the original cable design, Washington's father had specified cables substantially stronger than the calculated minimum required, provided the margin that allowed the inferior wire to be incorporated without compromising the bridge's safety. The design's conservatism, which had seemed excessive to some reviewers when it was established, was the factor that allowed the fraud to be absorbed without the catastrophic consequence of cable replacement. Emily communicated this conclusion to the bridge board with technical documentation that explained the analysis and supported the recommendation that construction proceed without cable replacement. She navigated the political response, the legitimate public concern about wire quality in a public safety structure, by providing transparent technical explanation of why the safety margins remained adequate. The bridge board accepted the recommendation. Hay lost his contract. Construction continued. The episode demonstrated something that the subsequent history of the bridge's completion confirmed. Emily Roebling was not delivering Washington's decisions. She was making engineering decisions, consulting with Washington when his health permitted, and taking responsibility for the outcomes.
The opening of the Brooklyn Bridge on May 24, 1883, was among the most celebrated events in American public life to that point. President Chester Arthur attended. The governors of New York and New Jersey attended. An estimated 153,000 people crossed the bridge on its first day of public operation. The official ceremonies involved Washington Roebling and not at all. He watched from his window in Brooklyn Heights, too ill to attend. Emily Roebling was the first person to cross the Brooklyn Bridge in a formal crossing. She rode in a carriage carrying a rooster, a symbol of victory, and the crossing was understood by those present as a recognition of her role in the bridge's completion. The recognition was partial and unofficial. The formal record of the bridge's construction identified Washington Roebling as chief engineer and gave appropriate credit to C.C. Martin and other subordinate engineers. Emily's name appeared in the contemporary press coverage, but not in the official engineering history. The congratulations offered to the Roebling family acknowledged Washington's leadership, with gracious references to Emily's assistance. The distinction between assistance and leadership was not one that the formal record had the conceptual framework to make, because the formal record operated within the assumption that a woman in Emily Roebling's position was assisting. The evidence that she was leading was in the notebooks, a technical record that the official history did not consult, partly because the official history was written within a decade of the bridge's completion, and partly because the conceptual framework for evaluating the notebooks as evidence of engineering authority did not exist until the late 20th century. The address that Emily delivered to a meeting of the American Civil Engineers in 1882, the year before the bridge's opening, at a meeting that was one of the very few occasions on which a woman addressed that organization in the 19th century, was an engineering presentation about the bridge's cable construction, the wire specifications, and the load calculations. It was not an account of her husband's engineering work. It was a presentation of engineering work that she understood as well as anyone present. The ASCE members who heard the presentation treated it as an interesting exception to the normal order of things, rather than as evidence of engineering capability that should revise their understanding of who was actually doing the engineering on the Brooklyn Bridge. This was not malice. It was the specific cognitive limitation of people who had a strong prior belief about what engineers looked like and who processed evidence that contradicted the prior as an exception rather than as a correction.
Emily Warren Roebling lived until 1903. She died 20 years after the bridge's opening, having earned a law degree from the New York University School of Law in 1899, one of the first women admitted to that program, and having continued the public and organizational work that had characterized her involvement with the bridge. She did not, in the years after the bridge's completion, seek formal recognition of her engineering role. She wrote about her experience with the bridge, but the writing tended to foreground Washington's contribution and to present her own role in the terms that the era's conventions provided, the devoted wife who had supported her husband through illness. The conventions were not false. She was devoted, and Washington had been ill, but they were incomplete in ways that the notebooks documented, and that Emily, writing within the conventions of her era, did not fully articulate. Washington Roebling lived until 1926. In the decades after the bridge's completion, as his health partially recovered, he participated in discussions of the bridge's history and provided accounts of the construction that acknowledged Emily's role without fully characterizing its extent. His characterization was always that she had been invaluable, that without her, the bridge would not have been completed. He did not characterize her as the effective chief engineer, but his statement that she had been invaluable, from a man who understood what engineering the bridge had required, was a more honest assessment than most of the official histories provided. The notebooks were donated to Rutgers by the Roebling family in 1966. They were cataloged as personal papers, correspondence, diaries, family records. The technical content was not fully recognized or analyzed until scholarly attention to women's contributions to engineering and science became a serious academic enterprise in the 1970s and 1980s. Historian David McCullough's 2072 biography of the Brooklyn Bridge, The Great Bridge, gave Emily Roebling more sustained attention than any previous account, characterizing her role as essential and drawing on the contemporary record to document her activities during the construction period. McCullough did not have full access to the Rutgers notebooks, and his account, while substantially more complete than previous histories, still operated within the framework of Emily as Washington's papal representative, rather than Emily as an independent engineering authority. The fuller reassessment came later, from engineering historians who analyzed the notebooks directly and who applied the technical knowledge required to recognize that the calculations and analyses they contained were not transcriptions of someone else's work, but original engineering.
The Brooklyn Bridge stands today as it stood in 1883. The towers, the cables, the deck modified and upgraded, but the essential structure unchanged. The load it carries has increased enormously from what was anticipated in 1883. The automobile traffic that was not imagined when the bridge was designed now crosses daily in volumes that the original calculation never contemplated. The cables have held. The towers have held. The anchorages have held. The structure that was designed with safety factors that seemed excessive in 1869 has proven adequate for demands that could not have been predicted in 1869. The conservatism of the original design, John Roebling's insistence on cable strength substantially beyond the calculated minimum, has provided the margin that accommodated the wire fraud, that accommodated the increased loads, that allowed the bridge to serve for a century and more beyond its original design expectations. Emily Roebling's contributions to the bridge's completion were not structural in the physical sense. The cables were designed by John Roebling, and the specifications were his. The towers were designed by Washington Roebling, and the proportions were his. The fundamental engineering that determined the bridge's structural character was the work of two men, father and son, one of whom died before construction was well underway, and one of whom was incapacitated for most of the construction period. What Emily contributed was the translation of that engineering into the completed structure, the supervision of construction, the quality control of materials, the political management that kept the funding flowing, the technical judgment that resolved the crises that arose during 11 years of construction in difficult conditions. This is a form of engineering that the formal records of the 19th century did not know how to credit to a woman. The notebooks know how to credit it. The notebooks are the record of a working engineer, someone who understood the mathematics, who interpreted the testing data, who calculated the loads, who made the judgments that the construction required. The bridge exists because of John Roebling's design and Washington Roebling's construction management during the years when he could exercise it.
The bridge also exists because of Emily Roebling's 11 years of work that the historical record described for nearly a century as assistance.
The notebooks are at Rutgers. They are available to researchers. The handwriting changes from the careful penmanship of a student to the confident notation of an engineer. The calculations are correct. The judgments they documented were the right judgments. Emily Roebling crossed the Brooklyn Bridge first, carrying a rooster in a carriage on a May afternoon in 1883. The bridge she was crossing was, in ways that the people watching did not fully understand, her bridge, not only in the sense that she had helped complete it, but in the sense that her engineering judgment had shaped its completion at every critical moment for 11 years. She did not say this. The conventions of her era did not provide a way to say it that would have been heard. The notebooks say it. The bridge says it, in its continued standing.